we know what's going on. So basically what you need to do is to just change the dates to, you know, what would have been today's class. If we didn't have the fire alarm, we would have been on modeling using exponential functions. That would have been today, but we're one class behind. So if you change December 7th to the 9th, December 9th will be now Monday's class instead of today's class. The 12th will be the 14th, and the 14th will be the 16th. So we will still have enough time to get in the last 4 classes. As you know, I had that TBA in there anyway, just in case we had a snow day. I wasn't planning on a fire alarm. So in terms of your assessments, remember, next Wednesday, we'll see how I took take-home quiz 4 distributed, and I put an arrow up here. Next Wednesday, I will give you a take-home quiz, and it will be due on Friday. So next Wednesday is your take-home quiz, and it's due on Friday. We will still have our review for the final on the last day of class, which is the 19th. That's still sacred. We didn't lose that, thank goodness. And again, I just want to reiterate that Project 4 is due that last day. However, if you want to get feedback on your project, the earlier you get it to me, the better. Okay, you now have all of the tools and skills to do this particular project. You don't have to wait to the end of the semester to do it or the last weekend. So if you want to do it early and get it in, I can grade it and get it back to you, and then you'll have that information for the final exam, which is what this is doing. It's helping you review some of the ideas we had for the final. Okay, is everybody clear on that? So I would love to see these projects floating in early next week. If that would be great, if you could get them in. But again, no pressure. It's just I want to be able to get the feedback to you. All right. So today I don't even want to start with the preview activities today. I want to jump right into the class activities number 4. This is where I want to start our class, because I want you to see why we need to know how to solve exponential equations. Because if you recall, we can't answer a question about how long it's going to take something, whether we're looking at money being put into some type of savings account or investment account, and if we ask the questions, how long will it take for that money to double? Or how long will it take for that money to reach a certain amount? If we had some type of fixed interest rate, we could determine that. However, you haven't learned how to solve equations like that until now. You now have all the tools you need in order to take an exponential equation and solve it for the variable, which is now the power, which we could not do before algebraically. So let's start with this problem. We remember our rabbit population problem. We worked with that rabbit utopia problem, and we started with 1,000 rabbits. And remember, 1,000 is what we call our initial value. That's our beginning spot. And that's always when time is equal to 0. So the models that we're going to work with now, you can use any letter you want. A of t for amount, Q of t for quantity, P of t for population. It doesn't matter. And then you always have some, remember the models that we were working with when we were just doing regular old exponentials look something like that, a times b to the x. So now each of these are going to have some meaning. So the a is always going to be your initial amount. So we usually use the notation something like this, a with a little 0 down there. That's read a sub naught. That means your initial amount. Okay, times, and then we have some base of our exponential raised to the power of t, because we're looking at time here. So our independent variable is t, not x. Now again, I just want you to see it doesn't matter. We could say q of t. Let's suppose we're looking at the number of cells in a petri dish that's growing over time. Then I might change the a to a q sub naught times b to the t. If I was looking at a population problem, it might say P of t equals P sub naught times B to the t. It just depends on the story you're telling in the application, okay, what what variables you use. So let's take a look. Let's work with this first model here. And let's put in to this equation in this function the information we have here. Yep, Jordan? We're on number 4 of the class activity. Could someone tell them the page? Oh, we didn't put page numbers? Okay. Sorry. Okay, so let's use this formula and let's start to work on this. So we know A sub naught from the very first sentence is 1,000. If we're doubling every year, what's our base for this exponential? 2 to the t. All right. So that's how we deal with this. Remember our rabbit population that started with 1,000 rabbits and doubled every year. That's all taken care of right here with this expression on the right-hand side of the equation. We've used that information. Now it asks how many years, so we're solving for t, solve for t, will it take for the rabbit population to be 50,000? So where do I put the 50,000? Yep. Go ahead, Colin. In front. So what am I substituting 50,000 for? A of t, right? A of t. We want to know when, so we're trying to solve for that thing, will the number of rabbits be 50,000? So now this is what our equation looks like. Okay. So let's solve this equation. We have an equation. We call this equation an exponential equation because our variable we're trying to solve for is an exponent. So this is what an exponential equation looks like. And we've had a look at several days of prop and graphs of exponentials and learning how they operate. And in order to solve this type of equation, this was one of the purposes we've had to go through all of that work. So we can actually answer a question like this. So when you have an exponential equation, you want to isolate your exponential expression. You want to get that all by itself on one side of the equation. So isolate, that's what isolate means. Isolate the exponential expression. In this case, that expression is 2 to the t. Okay. So to do that, we divide both sides by the coefficient, which is 1,000. So I'm going to divide both sides by 1,000. And on the left-hand side, I get 50. And on the left-hand side, I get 2 to the t. So let's just, like knowing what we know about the doubling function, let's just do a quick estimate for where, maybe we can get 2 values of t that our answer should fall between. So we know that 2 to the t looks something like this, where it goes through 0, 1. When t is 0, this is 1. And then it goes through 1, 2, and 2, 4, etc., etc. And out here we're at 6. 2 to the 6 is what? 2 to the third times 2 to the third. So that's 64, right? And we can keep going. Yep. Yeah, this is, can we just hang on for a second, okay? So right now we can at least get an estimate. So when t is 6, my answer would be 64. So that's too many years, right? And when t is 5, it's going to be 32. So we know our answer has to be somewhere, t has to be somewhere between 6 and 5. So that when we actually do our calculations with our calculator, we can at least have an idea of what our answer should look like. So the only way we can solve this equation, look at the previous step. We undid multiplication of 1,000. We undid that by dividing by 1,000 because that's the inverse operation of multiplication by 1,000. We don't even think about it anymore because it's so familiar to us. And hopefully between this class and particularly if you go on to 108, when you see something like this and you say, I need to solve this equation, I have to undo the exponential expression here, 2 to the t, and the only way to do that is with its inverse, which is log. Well, its inverse is log base 2. But guess what? Our calculator doesn't give us log base 2, right? It only gives us log base 10, which is called the common log, and the natural log. So just like with the equation that preceded this, whatever you do to one side of the equation, you do to the other. So I'm going to take the log of both sides, and it doesn't matter which log I take. And that falls from the change of base formula. If you ever look back and you want to see why this works the way it does, I can show you. So for now, all you need is a process of how to get that t so that we have a solution here. So take the natural log of both sides. Take the common log. It does not matter. So let's take the natural log, both sides. So you literally just put the natural log in front of the 50 and the natural log in front of 2 to the t. And I want you to realize that you could have also, if you wanted to, have put the common log in front of both. It does not matter. You could solve this either way. You get exactly the same answer. Now, this is where that wonderful property of logarithms come in. That third property of a power to a power, because that allows us to take this t and bring it right down in front, like this. Now, it's a linear function. It's just some number times t. That number happens to be this funky looking thing called the natural log of 2, which is about 0.69, blah, blah, blah. It's a messy number. But it's just a number multiplying t. So to solve for t, you just divide both sides by the natural log of 2. I don't want you to get like all freaked out when you see these things like natural log of 2 and natural log of 50. They're just constants. They're just numbers. They're a little messy, but they're just numbers. So you divide both sides by the natural log of 2. And there's your answer, folks. That's your exact answer. T equals the natural log of 50 divided by the natural log of 2. Okay? The natural log of 50 divided by the natural log of 2. Now, this is the exact answer. If I ask you for an approximation so that you could like write a little sentence, you just take out your handy dandy calculator and you say, okay, where's the natural log function? It's over here, ln. So I say ln of 50 divided by ln of 2. And we know our answer has to be somewhere between 5 and 6 because we estimated that at the beginning. So let's see what our exact answer is. Well, we can only get a decimal approximation. 5.64385,619 years. So t, now you write t is approximately, and depending on whether I ask you to round this or not, I'll tell you how many places, like to the 100th place. So if I ask you to round this to the 100th place, you would say, okay, I want to round it to the second place, and the number after 4 is 3, so I'm going to say 5.64. That's the value of t, and my answer, therefore, would be 5.64. I'd put approximately 5.64 years. Okay? So now we have the power to answer this question. Okay, we have the power to answer this question. Yep. It's not possible to do this without a calculator. There's no way you would know this answer without using a calculator. And, you know, part of it is you would have to know what log of 50 base 2 is, and you don't know what that is. And it even looks funky when you change the base to this. So I just want to convince you over here that t equals log base 50 over log base 2 gives you exactly the same answer if you use the common log. So let's bring up this calculator again. So you can see that it doesn't matter whether you take the common log or you take the natural log of both sides. You'll get exactly the same answer. There you go, 5.64. Okay, so again, whatever base you want to use, the common log or the natural log. The tendency is to use the natural log. That's just the standard practice. Unless you see something with base 10 here, then you would use the common log, right? If you had 10 to the t here, you would take base 10, the common log of both sides. If you have a continuous growth problem where your base is e, then the natural log is it's the exact inverse. So you wouldn't be looking at anything like this, because when you take the natural log of e, you get 1, because e to the first is e. So the reason we do everything we do is so that we can answer problems like this. And I wanted to start you off with this problem. So if we go back to the first problem in our demo, you can look at that problem right now and tell me that the answer is what? What's the answer to that? 2 times what gives you 50? 2 times 25, right? And the answer 2 comes from, that's the right answer, Jordan, because you were thinking 5 squared, right? So Jordan was already ahead one step and said the answer is 2, x is 2 here, because 2 times 5 squared is 50. So we know the answer to this, so there's no big surprises. However, let's change it to a funky number. Give me another number other than 50 over here. 75. 75 going once, 75 going twice. Okay. So if we had something like this, all we could do again is estimate. And again, we could do the same thing. If x was 2, we would be at 50, which is too small. If x was 3, we'd be at 250. So it's got to be a number between 2 and 3, and it's a lot closer to 2 than it is to 3. So again, we'd go through the same procedure. We want to isolate. Let's just review what we just did. We want to isolate this all by itself. To do that, you divide both sides by 2, and you get 5 to the x equals 37.5. And you divide both sides by 2. Okay. Now our big job is to undo the exponentiation. Okay, if I spell that out, exponentiation. Is that right? Yeah. Okay. So we want to get that value of x out of the sky there. We want to bring it down to earth. We want to ground it. All right? And the only way we can do that is with the log property. So again, I'm going to take the natural log of both sides. I'm just going to scoot a little ln in front of 5 to the x. Okay, just scoot a little ln in front of the values on both sides of my equation. There we go. 5 to the x, 37.5. I just want you to look at this right-hand side for 1 second. So this is saying the answer to this is some messy number because we're raising e, which is the base, to some power to get 37. Remember, e is a little bit bigger than 2, 2.718, something like that. So this is just a number over here. This is your input into your log function. This would be your x value. And what comes out of your log function is the exponent, right? But you might hear me sometimes say a word called argument instead of input, because that's what this is called. It's the argument. Just like this is the argument. But we've been saying input, output, input, output. And I just want you to know that if I say argument, I'm referring to the input. And that term is used a lot more when you work in pre-calculus with trig. So what's the nice thing about taking the natural log or the common log of both sides? It allows you to bring this exponent down in front, and then you can solve your problem. And that is a wonderful thing. So this exponent with the log property of the power property of logs comes down in front. And what am I left with? Just the natural log of 5. Just the natural log of 5. Now, the natural log of 5 is e raised to what power gives me 5? And I don't know that off the top of my head, but we don't need to know it. because we're just going to use our calculator to find the answer. So now, again, don't let these natural logs and logs mess with you. It's just a number. This is just a number. Just a number. So it's acting like the coefficient. It is the coefficient of x. So to undo it, you divide both sides by the natural log of 5. So x is the natural log of 37.5 divided by the natural log of 5. This is the exact answer. If I ask you for the exact answer, this is what I want to see. If I ask you for an estimate, rounded to 2 decimal places, then you would put this into your calculator. Natural log of 37.5 divided by the natural log of 5. And we know it's between 2 and 3, and there's our answer. So x is approximately 2.25. Okay? That's how you solve an exponential equation. You take the log of both sides. Now look at this right here, just for a second. See if you can see the forest through the trees. 5 to the x equals 37.5. Look at our answer. The natural log of 37.5, the natural log of that divided by the natural log of the base. Anytime you can recreate, you can isolate this, and you have some number raised to your variable equals another number over here. This is always what your answer is going to look like, whether it's the natural log of both of those numbers being divided or the common log. So it's once you do this a couple of times, you'll feel more comfortable with it. Yep, Jacob? Well, if this was e to the x, like, then I would definitely use the natural log. Right now, I have a choice whether to use natural log or common. But if it was e to the x, I would definitely use natural log, because look what happens. If you have e to the x equals 50, for example, you could take the natural log of both sides, or you could take the common log of both sides. You could take log base anything of both sides. But we have a button on our calculator that's the inverse of this. The inverse of e to the x is the natural log of x. That's the inverse. And if you ever forget, folks, look at your calculator. It tells you right here, look, ln, look at the little yellow button above it. That's the inverse of the natural log, e to the x. Look at the common log. What's its inverse? 10 to the x. Right? So if you had something like this, you would definitely want to put ln in front of each of these like this. And then look what happens. It's kind of really cool. The x comes down in front, multiplies the natural log of e, equals the natural log of 50. Well, the natural log of e, remember, the natural log of e looks like this, log base e of e to the 1. That's what it looks like. So you just lift off your 1. This is a big fat 1. Here's your answer. X equals the natural log of 50. So if it had a base e, I definitely would use the natural log. I would take the natural log of both sides, right? It just because everything falls away because the natural log of e is the number 1. So it's a very quick solution that way. You don't even have to use your calculator there. Okay. Other questions? Okie doke. So let's take a look at a log equation. So a log equation is really easy to spot because it has a log in it. Okay, that's no surprise. And some of you might think, oh no, a log equation, it must be really hard to do, especially after all this work I had to do with the exponential equation. But guess what? Log equations are easy to do because you can convert every single log to an exponent. An exponential equation, every log equation to an exponential. So these actually are a bit of a surprise for us because they can be done fairly quickly. So let's look at this. 2 times the log of 5x equals 4. So again, I want to isolate my log expression. So I want to isolate this. Okay. And one way I can do that is what I always am used to doing if that's the information I'm interested in solving for. Look, our x is now buried inside a log, right? It's now inside that log, so we got to do some work to get it out of there. So first we want to remove any extraneous material around it, right? We've got to remove all the leaves to get inside that log, so we're going to divide both sides by 2. So we get log of 5x equals 2. Now, the reason we had to spend all that time writing log equations as exponential equations is so we could do this solution very quickly right now. What's the base on that log, even though I don't see it? 10. If you want to, go ahead and put it in for yourself. It helps you. So a log is an exponent. 2 is the exponent of 10. That gives me 5 to the x. So you just write it as an equivalent exponential equation. So 10 raised to the second power gives me 5x. Holy schmoly, look how easy that is to solve. It's just a linear equation now. 100 equals 5x. X is 20. So exponential equations, you need to use logs to solve. Log equations, you can undo the log just by rewriting it as an exponential equation. So you always want to check, just like when we were way back in the first part of the course, and we got extraneous solutions, it's possible to get extraneous solutions to these equations as well. Okay? So 2 times the log of 5 times 20 equals 4. 2 times the log of 100 equals 4. This is the one I told you is to always put on the top of my paper because the log of 100 is 2. 2 times 2 is 4. I'm a happy camper. As you recall, we spent a whole day looking at log problems. We looked at expanding logs that were products or quotients or a power to a power, and we looked at then condensing them back. So we worked from left to right on these equations, and we worked right to left. We had a whole class filled with working with those properties. Today, this is the direction we're going to go in for the next couple of the next problem. All right, so if you look at this first problem here and you say, well, gee, I want to isolate my log expression, you say, uh-oh, I have a problem because I have a log on both sides of the equations. So the first thing you have to do is put all of your logs on one side, all your log expressions on one side of the equation, just like when you have an equation with x's in it and you have x's on both sides. So the first thing you want to do here is add log base 2 of x to both sides. Okay. And that gives me a 2 on the left side, and then it gives me a sum on the right side, a sum of 2 logs with the same exact base. I'm adding 2 logs. In my mind, I think about when do I add exponents? Oh, when I multiply. And that takes me right back to this property. When I have log base b of u plus log base b of v, that's the same thing as log of that common base of u times v. So now I'm going to use my log property, the product rule for logs, to combine this. I want to rewrite this as 1 log. It's a single log. I want to condense it. So this equals log base 2 of 4x times x. Just multiply that. And I can rewrite that as 4x squared. So I had to do 2 steps before I could isolate my log. Okay, first I had to get all my logs on one side. Then I had to use one of my properties to squish it into one log. Okay. Now it's a piece of cake because all you do now is you say, I'm going to rewrite this as an exponential equation. I know what my base is. I got to change this next year so I don't have all these 2's floating around. So my base is 2. So the base on my exponential equation is 2. The exponent on my base is the answer to my log, and that will bring me back to 4x squared. So now this is 4 equals 4x squared. This is a quadratic equation. Now that we've looked at polynomial functions and zeros and the numbers of zeros and the number of factors we can have, we know how many solutions to a quadratic equation. How many zeros? At most. 2 real zeros, right? So that's a reminder to be looking for 2 solutions. Look for 2 solutions. So when you divide both sides by 1 and you get x squared, you don't say x squared is what? No, what? No, that's what I want you to say. I want you to say it's plus or minus, right? 1. That's the part we always forget, the plus and minus. But again, I want to just reiterate, when you see an equation like this, to solve any quadratic equation, set it equal to 0, and you can either use your quadratic formula, or in this case, you would factor, because that's really a quick factoring of these 2 conjugates. So x is plus or minus 1. That way you would never miss the fact that it has 2 solutions, right? So this is where the check really comes into play, right here, right now. Because if I were to graph this log, what was the base? Base 2. All right, really the base doesn't matter that much, at least just in terms of a picture. Remember, a log only uses a basic parental log. Jacob, he's trying to ignore you, okay, what you're saying, because he's trying to pay attention. Okay. So remember, your log has a domain of all positive numbers in a range of all real numbers, and it happens in the first and fourth quadrants. So your log function looks like this. Okay. Goes through 1, 0. And in this case, if it's log 2, it would go through 2, 1. And then we can play the game from there. So the point here that I'm trying to make is your input into a log, your input, which is that stuff in parentheses, must be positive. In order for you to be able to get an output, okay? This part of the graph doesn't even exist. So when you take a look at these 2 answers, you don't just say to yourself, oh, because I have a -1, it's not going to work. It depends on what your input looks like, but we're going to check it. So we go back to our original equation, and that's where we always go back to our original equation, because if we made a mistake in our algebra on the way down to get solving for x, and we don't use the original equation, then we won't find our error. So 2 minus log base 2 of 1 equals log base 2 of 4 times 1. Log base 2 of 4 is log base 2 of 4, 2, because 2 squared is 4. Log base 2 of 1 is 0, because 2 to the 0 is 1. 2 equals 2. I'm a happy camper. Okay, now I go to check my other answer. The minute I go to put my -1 in there, I go, no way, I can't have a negative log. Not going to work. So my only answer to this solution is x equals 1. -1 is extraneous. It's not a solution to our original equation. Now, this is the little trap I do not want you to fall into. Okay, the little trap I do not want you to fall into is the following. If I had an equation, I'm just making this up right now. Let's suppose I had that on one side and blah, blah, blah on the other. And I got x equals -2 for one of my solutions. This is a if. You don't just say, oh, x is -2, I don't have an answer. Because you always have to go back to the original equation. And when you look at your input or your argument here, and you put the -2 in for x, what does this become? 8, which is positive. So that's okay. The -2 would work here. Okay. So you just don't look at your answer and say, oh, if it's negative, it's just not going to work. You have to go back to your original equation and take a look at your expression that's your input and put the variable in. And if it's negative, when you do whatever operations it tells you to do, then you say that's an extraneous solution. That's not a solution. Okay, because I can never have a log take the log of a negative number. I think you're all set now for your activities. What I want you to do is to cross out this activity, give you a little, and then I want you to change this first one to be 5 to the x equals 70. Okay, I just want you to change it. After doing this in class the other day, I just rethought the whole thing there and how I wanted to start. So there you go. 5 to the x is 70. That's an exponential equation. You'll need, that's very close to the one we did. Cross off this one, and here's one, another exponential equation that you're going to need to use your logs with. And then after that, you have some log equations, and then I call this section oleo, which mixes things up a little bit. They're a little harder. We've already done the application problem, and here's another application problem. So you have 35 minutes. I think that's plenty of time. I'm probably going to stop you about 1/4 to talk to you a little bit about your tests, which were overall excellent. As usual, you outperformed my other class. Your median grade was an 80, which is really fantastic for this test. This test is not usually a very good test for the semester because the material is harder than all the other tests. But as usual, I'm very pleased with the work this class is doing. So it was good results, and I'll talk to you about a couple of problems either today or during the final review. Any questions before we close for the day and start? Yep, Jordan? Yep, I can go get them.